The Mpemba effect, named after Erasto Mpemba in 1969, is the observation that, in some circumstances, warmer water can freeze faster than colder water. Although there is evidence of the effect, there is disagreement on exactly what the effect is and under what circumstances it occurs. However, in 1966 Keith Hauser, a senior at Port Washington High School in Ohio, entered the Ohio State Science Fair proving warmer water he used in the winter for cattle froze quicker than cold water. There have been reports of similar phenomena since ancient times, although with insufficient detail for the claims to be replicated. A number of possible explanations for the effect have been proposed. Further investigations will need to decide on a precise definition of freezing, and control a vast number of starting parameters in order to confirm or explain the effect. Definition. Zheng proposes as a more precise wording. There exists a set of initial parameters, and a pair of temperatures, such that given two bodies of water identical in these parameters, and differing only in initial uniform temperatures, the hot one will freeze sooner. However, even with this definition, it is not clear whether freezing refers to the point at which water forms a visible surface layer of ice, the point at which the entire volume of water becomes a solid block of ice, or when the water reaches 0 degrees Celsius. A quantity of water can be at 0 degrees Celsius and not be ice. After enough calories have been removed to reach 0 degrees Celsius, more calories must be removed before the water changes to solid state. So water can be liquid or solid at 0 degrees Celsius. With the above definition, there are simple ways in which the effect might be observed. For example, if the hotter temperature melts the frost on a cooling surface and thus increases the thermal conductivity between the cooling surface and the water container. On the other hand, there may be many circumstances in which the effect is not observed. Observations. Historical context. Various effects of heat on the freezing of water were described by ancient scientists such as Aristotle. The fact that the water has previously been warmed contributes to its freezing quickly, for so it cools sooner. Hence many people, when they want to cool water quickly, begin by putting it in the sun. So the inhabitants of Pontus, when they encamp on the ice to fish, pour warm water round their reeds that it may freeze the quicker, for they use the ice like lead to fix the reeds. Aristotle's explanation involved antiperistasis, the supposed increase in the intensity of a quality as a result of being surrounded by its contrary quality. Early modern scientists such as Francis Bacon noted that slightly tepid water freezes more easily than that which is utterly cold. In the original Latin, aqua parum tepida facilius conglaciatur quam omni no frigia, René Descartes wrote in his discourse on the method. One can see by experience that water that has been kept on a fire for a long time freezes faster than other. The reason being that those of its particles that are least able to stop bending evaporate while the water is being heated. This relates to Descartes' vortex theory. James Black investigated a special case of this phenomenon comparing previously boiled with unboiled water. The previously boiled water froze more quickly. Evaporation was controlled for. He discussed the influence of stirring on the results of the experiment, noting that stirring the unboiled water led to it freezing at the same time as the previously boiled water, and also noted that stirring the very cold unboiled water led to immediate freezing. James Black then discussed this Fahrenheit's description of supercooling of water, arguing, in modern terms, that the previously boiled water could not be as readily supercooled. Mpemba's observation. The effect is named after Tanzanian Erasto Mpemba. He described in 1963 in Form 3 of Magimba Secondary School, Tanganyika, when freezing ice cream mix that was hot in cookery classes and noticing that it froze before the cold mix. He later became a student at Mkwawa Secondary School in Iringa. The headmaster invited Drive. Dennis G. Osborne from the University College in Dar es Salaam to give a lecture on physics. After the lecture, Erasto Mpemba asked him the question: if you take two similar containers with equal volumes of water, one at 35 degrees Celsius and the other at 100 degrees Celsius, and put them into a freezer, the one that started at 100 degrees Celsius freezes first. Why? Only to be ridiculed by his classmates and teacher. After initial consternation, Osborne experimented on the issue back at his workplace and confirmed Mpemba's finding. They published the results together in 1969, while Mpemba was studying at the College of African Wildlife Management. Modern context: Mpemba and Osborne describe placing 70 ml samples of water in 100 ml beakers in the icebox of a domestic refrigerator on a sheet of polystyrene foam. They showed the time for freezing to start was longest with an initial temperature of 25 degrees Celsius and that it was much less at around 90 degrees Celsius. They ruled out loss of liquid volume by evaporation as a significant factor and the effect of dissolved air. In their setup, most heat loss was found to be from the liquid surface. David Auerbach describes an effect that he observed in samples in glass beakers placed into a liquid cooling bath. In all cases the water supercooled, reaching a temperature of typically -6 to -18 degrees Celsius before spontaneously freezing. Considerable random variation was observed in the time required for spontaneous freezing to start, and in some cases this resulted in the water which started off hotter freezing first. In studies appearing in phys.org, James Brownridge, a radiation safety officer at the State University of New York, indicates supercooling is involved. Suggested explanations. The behavior seems contrary to natural expectation, but many explanations have been proposed. Evaporation. The evaporation of the warmer water reduces the mass of the water to be frozen. Evaporation is endothermic, meaning that the water mass is cooled by vapor carrying away the heat. But this alone probably does not account for the entirety of the effect. Convection. Accelerating heat transfers. Reduction of water density below 4 degrees Celsius tends to suppress the convection currents that cool the lower part of the liquid mass. The lower density of hot water would reduce this effect, perhaps sustaining the more rapid initial cooling. Higher convection in the warmer water may also spread ice crystals around faster. Frost has insulating effects. The lower temperature water will tend to freeze from the top, reducing further heat loss by radiation and air convection, while the warmer water will tend to freeze from the bottom and sides because of water convection. This is disputed as there are experiments that account for this factor. Supercooling. It is hypothesized that cold water, when placed in a freezing environment, supercools more than hot water in the same environment, thus solidifying slower than hot water. However, supercooling tends to be less significant where there are particles that act as nuclei for ice crystals, thus precipitating rapid freezing. Solutes. The effects of calcium carbonate, magnesium carbonate among others. Thermal conductivity. The container of hotter liquid may melt through a layer of frost that is acting as an insulator under the container, allowing the container to come into direct contact with a much colder lower layer. That the frost formed on the container now rests on a much colder surface than the originally colder water, and cools far faster from this point on. Dissolved gases. Cold water can contain more dissolved gases than hot water, which may somehow change the properties of the water with respect to convection currents, a proposition that has some experimental support but no theoretical explanation. Recent views. A reviewer for Physics World writes, even if the Mpemba effect is real, if hot water can sometimes freeze more quickly than cold, it is not clear whether the explanation would be trivial or illuminating. He pointed out that investigations of the phenomenon need to control a large number of initial parameters and need to settle on a particular method of establishing the time of freezing, all of which might affect the presence or absence of the Mpemba effect. The required vast multidimensional array of experiments might explain why the effect is not yet understood. New Scientist recommends starting the experiment with containers at 35 and 5 degrees Celsius to maximize the effect. In a related study, it was found that freezer temperature also affects the probability of observing the Mpemba phenomena as well as container temperature. For a liquid bath freezer, a temperature range of -3 to -8 degrees Celsius was recommended. In 2012, the Royal Society of Chemistry held a competition calling for papers offering explanations to the Mpemba effect. More than 22,000 people entered, and Erasto Mpemba himself announced Nikola Bregovic as the winner, suggesting that convection and supercooling were the reasons for the effect. Similar effects. Other phenomena in which large effects may be achieved faster than small effects are latent heat. Turning 0 degrees Celsius water to 0 degrees Celsius ice takes the same amount of energy from the water as cooling it from 80 degrees Celsius to 0 degrees Celsius. Leidenfrost effect. Lower temperature boilers can sometimes vaporize water faster than higher temperature boilers. Region beta paradox. People can sometimes recover more quickly from more intense emotions or pain than from less distressing experiences. Bibliography. Dorsey, Ernest. The Freezing of Supercooled Water. Trans. Am. Phil. Soc. 38. 247-326. DOI 10.2307 1005602. JSTOR 1005602. An extensive study of freezing experiments. Auerbach, David. Supercooling and the Mpemba effect. When hot water freezes quicker than cold. American Journal of Physics 63. 882-885. Bibcode 1995 AMJPH 63 882A. DOI 10.1119 1.18059. Auerbach attributes the Mpemba effect to differences in the behavior of supercooled formerly hot water and formerly cold water. Knight, Charles A. The MPEMBA effect. The freezing times of hot and cold water. American Journal of Physics 64. 524. Bibcode 1996 AMJPH 64 524K. DOI 10.1119 1.18275. Monhe, Zheng. The Mpemba effect. When can hot water freeze faster than cold? American Journal of Physics 74. 514. Arxiv Physics 05122262. Bibcode 2006 AMJPH 74 514J. DOI 10.1119 1.2186331. Chone, Marcus. Why water freezes faster after heating. New Scientist.